So hello guys, welcome back to this series of videos on pre-stressed concrete. In the previous videos we have seen some introduction to pre-stressed concrete and some losses, some things related to losses. In the middle there comes a chapter which is called as analysis. So whenever you are viewing the video, please view analysis videos first and then go for losses videos, because that is going to help us to understand the losses in a better fashion. So let us start analysis of pre-stress by giving few assumptions. So what are the assumptions that are involved in case of analysis of pre-stress? So concrete is homogeneous and elastic material. As it is homogeneous and as it is elastic, you'll only use one E value, one G value, one mu value. All the elastic constants are going to be only single values. And then we are saying that it is also elastic. Elastic means we are able to apply Hooke's law, right? So these are the two implications of this assumption. Plane sections remain plane before and after bending. So this is the basic assumption that we have always made in case of strength of materials, and we are also making this assumption here. That means there are no shear stresses, which, or you can say there is no warping that is going to take place. And warping basically takes place because of the shear strains that are existing, or the shear stresses that are in the member. Next is variation in stress of steel due to the external load is negligible. So as in case of pre-stress, what you will do, you will stretch the steel before or after pouring the concrete. In both cases, when you load the beam or the girder, that external load will not have any effects on the stress that has been already supplied into the steel. Okay, let it be in the post-tensioned case or in the pre-tensioned case, it does not matter. If you have supplied 2000 MPa of the stress, that 2000 MPa will remain unaffected by the external load. That is the meaning. Next, stress in reinforcement does not change along the length of the member. Okay, so stress in the reinforcement is not going to change along the length of the stress in the reinforcement does not change along the length of the member. That means at x equal to 0 you are going to have same stress, at x equal to L also you are going to have same stress value. If you have stretched the steel, so let us say that I have a steel HT2350, that means the yield strength of this steel is how much? It is 2350 megapascals. Now as this is the yield stress, yield strength of the steel, we have say stretched this steel to 2000 Newton per mm squared. Okay, I have stretched this up to 2000. This stress will remain same throughout the member or throughout the length. Okay, so it will not change along the length of the member. Okay, so if at x equal to 0 you have this value of the stress, the same value of the stress will be there for x equal to L or x equal to L by 2. You can take any value of x, at that value you will find 2000 Newton per mm squared. Both, and this basically enables us to say that if the pre-stressing force, if the pre-stress would vary along the length of the member, then we would have taken different values of P values or different values of the pre-stressing force P at various other sections. That would complicate the process. Okay, we make assumptions. The main aim of making assumptions is to simplify the process, and that is what we are doing. We are saying that all the stresses or the stress along the length of the member is going to be same. That would mean essentially that we are simplifying the problem of taking different pre-stressing force at different sections. Then both steel and concrete behave elastically under service load and working stress or the working stress conditions. So this is another assumption. Part of the assumption was the first one, where both are being elastic. Okay, here in this assumption we have added steel to that elastic nature. So steel is also elastic, concrete is also elastic. Both are getting stretched by both will basically follow the Hooke's law. Elastic would mean both are going to follow the Hooke's law. Okay, then in order to do the analysis of pre-stressed concrete members, we have three concepts. So the first concept is stress concept, second concept is the load balancing concept, and the third concept is C line and P line concept. This is cable line and this is pressure line. So cable line and pressure line concept. So we have three basic concepts that will enable us to analyze a pre-stressed concrete beam or a gutter, or let us say in general a member. So essentially when we say analysis, we mean that we are going to find out the stresses at various sections. Okay, so you will be given some loading, you will be given some beam, all the cross section will be given, pre-stressing forces are going to be given, and then if you find out what is the stress at various cross sections, then that particular thing becomes the analysis of the pre-stressed concrete members, right? So let us start with the first one, that is stress concept. Okay, so this concept I think I have already discussed in one of my previous videos on introduction to pre-stressed concrete. When we were discussing this, okay, we did not know that it was a stress concept, but essentially it was a stress concept only. So whatever simplified things that you learn in the introductory part of pre-stressed concrete, they are based on stress concept. Let us see that stress concept. So let us apply that stress concept first for a concentric tendon. So what do you mean by concentric tendon? It will be along the centroidal axis or longitudinal axis of the beam. So let us say that this is the beam. Okay, so this is subjected to loading like this, right? And then you have a tendon which is along the centroidal axis like this. Now as it is along the centroidal axis, it is going to be concentric. Why it is going to be concentric? Because there is no eccentricity, and as eccentricity is not there, there are no moments due to pre-stressing forces. Only stresses that are going to come are one normal compressive stress, which is due to pre-stressing force, and second is the bending stress, which is coming due to the externally applied loads. Okay, so now as it is concentric like this, in this case, whenever we discuss a concentric case like this, and if P load is being basically applied, we find out the normal stress. We write the normal stress value as P divided by A, right? So this normal stress is basically assumed to be uniform throughout the member. Okay, so please don't confuse the neutral axis with this normal stress. So normal stress has got no meaning for neutral axis. Okay, neutral axis becomes useful in bending case, because in bending case you have a part in the beam wherein there are stresses wherein the stresses are equal to 0. That does not happen in normal stress. Okay, so normal stress is basically uniform throughout the depth, while bending stress is not uniform throughout the depth. It is going to variate linearly like this. Okay, so under this UDL that has been applied, the top portion will be in compression while the bottom portion will be in tension. While discussing pre-stressed concrete, contrary assumption will be taken. Okay, contrary sign convention will be taken, not assumption. What is the usual sign convention in strength of materials? Tensile stresses are positive, but here in this case we are going to take compressive stresses as positive. Automatically the tensile stresses are going to be negative, right? So because of this force applied UDL, the top portion is going to be in under compression because it is going to bend like this, and the bottom portion will be in tension. So this is, as it is going to bend like this, bottom portion is in compression, the bottom portion is in tension, and the top portion is in compression. So therefore this is the type of variation that we can plot. Now the value of the bending stress is obviously going to be my divided by I, and the final stress diagram that we have is this. Okay, and we always desire to have compressive stresses completely throughout the member cross section. Why? Because concrete is good in compression, we try to make use of that property, and in order to make use of that property we are basically pre-tensioning it, or using the pre-stressed concrete, right? Okay, so then what is going to be the value of F1 and what is going to be the value of F2? Okay, then stress concept is used to compare the calculated stresses with the allowable stresses. Now you can use this concept obviously, because you have some allowable stress value from whatever tests you have conducted. You know the allowable stress for the materials. In order to compare that allowable stress with the existing with the stresses that are going to come on the cross section, you can basically decide whether to go for this cross section or not. So F1 will be equal to what? P by A, as it is compressive, it will be positive, and the top fiber is in maximum compressive stress as far as bending stresses are concerned. So it will be plus my by I, and the bottom value F2 will be equal to P by A minus my by I, right? So these are the two values of F1, right? Okay, now next is what happens if you go for an eccentric tendon. So when you go for an eccentric tendon, right, you'll have different things. Like what we can do in eccentric tendon, you have some eccentricity, and after having some eccentricity, you have a cable on which you're going to apply your pre-stressing forces, correct? Now what we can do is, as the pre-stressing forces will be directed like this towards inside, we can write this here and here. So this forces, this P here and this P here, this P here and this P here. So these two forces together are going to form a couple. These two forces are going to form a couple, right? So this is also at E distance, this is also at E distance. So you'll have couples and a concentric force. So we are converting an eccentric tendon into a concentric tendon along with the moment that is due to the pre-stressing force. So finally what I can do, I can replace this P force here. I can shift this P force above and make it concentric, and in addition to that I have a moment PE which is getting applied due to the pre-stressing force, and then we make the analysis. So for concentric force, obviously we will have what? We will have this kind of a situation, okay, normal stresses, and these normal stresses are same throughout the member, or same throughout the depth of the section. Now the next is, you have a bending moment that is generated because of the pre-stressing force. The bending moment has the magnitude of P into E, and because of this bending moment, the top fiber is, and it is going to bend like this. Because of the bending moment, it is going to bend like this, right? And therefore you will have the top fiber in tension and the bottom fiber will be in compression. This happens because of what? This happens because of the bending moment that is due to the pre-stressing force. And therefore if you plot the variation of this bending moment due to the pre-stressing force, the top will be in tension, therefore it has been drawn as negative, and the bottom will be in compression, therefore it has been drawn as positive. Now PE is the moment value, so my divided by I. So this is the stress value that we are going to have as far as pre-stressing bending moment is concerned. Now due to externally applied load, we will have the same situation as in the previous case. Top fiber will be in the compression, bottom fiber will be in tension. So my by I is the magnitude of that stress, okay? So F1 value, and this is F2 value. So F1 value can be written over here, it is P by A minus PE y by I plus my by I. Second F2 is equal to what? It is P by A plus PE y by I minus my by I. Now you can see the benefits of having a eccentric tendon. So first benefit is, it is reducing the top compressive stress. So compressive stress is getting reduced as compared to the concentric tendon, and the compressive stress at the bottom is increasing, right? Now why this becomes the benefit? Because in the top, as the compressive stress is reducing, we will require low grade of concrete, okay, as compared to the concentric tendon. In concentric tendon, the stress values may reach so high values that they may only be sufficed by using M60 or M70 grade of concrete, okay. But as you are providing some eccentricity, because of that eccentricity there is a tensile stress that develops at the top, and which basically reduces your compressive stress and reduces your demand for high grade concrete. So you will now be referring, or you will now be going for M40 or M35. These grades of the concrete will now also be okay with us. So then that becomes more easy to make, as well as maintaining the quality control, and all the aspects of M40 and M35 are relatively easier as compared to M60 and M70. There are several other reasons behind using the high grade concrete also, okay. We cannot go lower than this because of the reasons like bearing stresses and the bond stresses that are basically transferring the pre-stressing force. They are going to be so high that they are not going to be sufficed by using M20 or M25. So therefore you will have the grade more than M30 always. Second is, it is increasing the compressive stress at the bottom. Now here there is a danger that this F2 value may become tensile like this, okay. It may become tensile, and we don't want that. And in order to ensure that this bottom fiber always remains in compression, we need to supply more compressive stress at the bottom, and that is what eccentricity has done for us. It has supplied more compressive stress at the bottom, which is ensuring, or basically which is taking us to the safety point where we are saying that only compressive stresses are being generated across the cross section, okay. Then the values I have already discussed, what is F1 and what is F2 in the previous slide. Let us now understand what is cracking moment. Okay, so this is a new concept, cracking moment. So bending moment at which cracks develop in the pre-stressed concrete. So this is the bending moment due to what? This is the bending moment due to basically externally applied live loads. Okay, usually you take live loads and externally applied moments, then only we define cracking moment. So bending moment at which cracks are going to develop in the pre-stressed concrete, that is going to be the cracking moment. Now when the cracks are going to be developed, obviously when your bottom fiber is going to be in tension, and that tensile stress which appears at the bottom is going to cross your allowable stress value of concrete in tension. What is allowable stress value of concrete in tension? That will be given by the modulus of rupture. Okay, generally we give the FCR value as 0.7 root FCK. If I am not wrong, this is the formula that we use in RCC. FCR is nothing but rupture stress. Okay, it is nothing but when concrete is subjected to bending, and in that case of bending, the tensile stress, maximum tensile stress the concrete can take, will be given by this particular formula. Okay, so if that value of concrete is exceeded, you will have cracks developed in the concrete. So visible cracks appear when the tensile stress at the soffit are approximately equal to modulus of rupture of the material. That is going to happen, right? When they are going to exceed the modulus of rupture, then you will have visible cracks getting developed. Then what is the load factor? Load factor is nothing but the factor of safety, you can say. It is a live load that is required for cracking divided by live load that is actually acting, right? So maximum live load that you can apply divided by the live load that is actually acting on the member. And as I told you already, in actual sense, cracking moment is defined for live loads. When you apply live loads, then the value of the live load at which the visible crack are going to appear is nothing but cracking moment. That means we are saying that it is an externally applied, it is the bending moment due to externally applied load, but in that we have to be specific. It is the externally applied live load that for which your cracking moment is basically defined. So the load factor value is equal to live load that is required for cracking divided by the existing live load. That will define obviously your factor of safety. So load factor is equal to live load moment required for cracking, and that is divided by actual live load moment. Many times the load factor is calculated in terms of total load also. So total moment, that is dead load and live load, which is required for cracking, divided by the total moment that is acting on the beam, right? So we are going to consider dead load plus live load also, and that is again divided by the total moment that is basically acting. Now whenever it is asked in the exam to write down the load factor, you will have to calculate the load factor on both the bases. So it is not like a signature that you don't only have live loads. Okay, you can find the load factor based on the total load also. So you'll have to find out these two things, the load factor based on these two criterion. Number one is based on live load only, number two is based on dead load plus live load. Okay, so this is our load factor. Fine, then let us go to various stages of pre-stressing. Okay, and from here you will basically understand that what I was talking about in the previous cracking moment. What is live load, what is dead load, and all these things. These things are considered in various stages of pre-stressing. So first stage is transfer stage. By the name itself you might have understood that this is nothing but the stage where pre-stressing force is basically transferred to the concrete. So at this stage, stresses due to pre-stressing force and the dead load are taken into account. So not only pre-stressing force, by the name you can understand that it is a pre-stressing stage where pre-stressing force are going to be transferred. But in addition to that pre-stress force, you are also taking into consideration the dead loads. Okay, so losses are not considered at this stage because now you have not started using because the time is not so high, or the age of the particular member is not so high, so that the losses can be taken into account. Therefore at transfer stage you are not going to take losses, right? You are going to take pre-stressing force and you are going to take dead loads. So therefore at transfer stage, if you write down for concentric tendon that we have discussed, the value of F1 will be equal to P by A plus MD, that is moment due to the dead load, into Y divided by I. F2 will be equal to P by A minus MD Y divided by I. In case of eccentric tendon, when you are looking for transfer stage, so it will be F1 will be equal to what? P divided by A, because this is due to pre-stressing, PEY by I because this is due to pre-stressing again, minus of PEY by I plus MDY by I. This is due to the dead load of the member. Then F2 is P by A plus PEY by I. Both these are due to the pre-stressing force. That means you have to take them into transfer stage, and then you will have another one, that is MDY by I. Okay, what about service stage? So at this stage, stresses due to pre-stressing force, dead loads, live loads, and even losses are considered. So stresses due to one, pre-stressing force, that means whatever the stresses are there in the transfer stage, in addition to those stresses you are also going to consider the stresses due to live loads and losses. Okay, so dead loads, you are going to consider pre-stressing force, you are going to consider dead loads, live loads, and even losses. Okay, even losses are going to be considered in the service stage. Okay, then for concentric tendon, if you write down the service stage equations, the F1 value is going to be P by A, which is due to pre-stressing force, MDY by I, which is again due to dead load, MLY by I, which is due to live load. Again the F2 value run in the similar fashion. Only thing is you are going to have negative values for the dead load moment and the live load moment. The reason is both the stresses are going to be tensile, right? Then in case of eccentric tendon, again in addition to this was discussed already in transfer stage, you are going to add what? MLY by I. And the same case here also, this was already discussed in the transfer stage. In addition to this, again you are going to deduct mly by I from that, because it is due to it, because it is tensile, which is due to live load. So all this calculated after accounting for losses in the prestress. Now this is very important, that whatever we are doing in transfer stage, okay, we are not going to write down directly P by A same as that we have written in the transfer stage. Okay, we are going to now change the P values. Say for example, the P value in the previous case when in the transfer stage was 1000 kilonewton, let us say. But when you write the equations for service stage, the P value has to be 800 kilonewton. That means you have accounted 200 kilonewton for what? Losses. So indirectly you are basically accounting for the loss as well, because you are reducing the pre-stressing force. As you are reducing the pre-stressing force, your losses are automatically accounted for. Okay, so this is about the service stage and the transfer stage. And therefore when you say the cracking moment case, cracking moment is only defined as far as live load is concerned. What is the additional live load that I can put, maximum live load that I can put, so that I do not have cracked concrete, right? In the similar fashion, then it was defined separately for the total load as well. Okay, fine. So the next is load balancing concept, which we will discuss in the next video. So thank you for watching this, and keep watching. And if you like the videos, please subscribe to the channel and share this with your friends. Thank you.